Welcome everyone. So my name is Arturo Klie. I'm Hector's son. Hector couldn't make it today. He's doing business in Brazil right now. So I'll attempt to fill in his shoes. So basically today we're going to talk about how to use a clustering method in a real-time analytics situation to basically do some production forecasting for oil and gas. So here's the agenda. We'll first talk about the motivation and why we're doing this. We'll talk about our clustering approach. Then we'll describe a little bit about the big data platform. And we'll do a short demo that we recorded on video. And we'll do some conclusion and answer any questions. So one of the reasons why we did this is because as we approach the Industry 4.0 era, we have more connected devices, more data flowing in, then it becomes a challenge to kind of process all this data in real time. So we need to build real-time solutions that can scale. So rather than having a human monitor all this production data daily basis or monitor the injection of fluids while you're fracking the well, or any other use case relative to real-time data analytics, a solution like this could be useful to basically grab time series data, several curves, kind of combine them into families of curves, and derive forecasting out of it. So we're going to talk about a clustering technique so that we can improve the resilience of this clustering method. So we do this basically by adding a preprocessor. We use the Procristes method to basically go ahead and grab several curves or several physical occurrences, and then we try to match them with as well as we can without severely altering the physical attributes in a curve. So you can imagine if we have several production curves, they would follow a physical trend, but some of them might have anomalies, so we can kind of isolate them into families of curves and use that, apply a prediction algorithm on top to improve our forecasting. So the reason why we want to do Procristes is because as we are doing these trial runs of the clustering process, the curves, every run will be a bit unstable. So you'll see here on the left, we have multiple runs with the same data set. On the left side, you see there's a bit of a inconsistency in the centroids of the clustering. And then on the right side, when we apply Procristes as a preprocessor, we tend to have more consistent centroids along the curves. So this is the basic prediction algorithm that we apply on top to kind of showcase the clustering method. So basically, all these blue curves represent the clusters that we generate, the family of curves that we identify. Then we apply a prediction algorithm that basically grabs the ratio between a certain set of curves where our current real-time data is flowing in. So as we'll show this in a bit in a demo, but basically as data flows in, we'll derive the ratio, we'll generate this prediction curve, and then we'll check the threshold to see if it's falling outside a certain threshold, then we'll recalculate that prediction using the clusters as a reference. So let me switch to the demo now. Okay. So I'll stop here and kind of explain what's going on. So this is actually a high-level view of the architecture for this demo. On the left side, you have a few data sources. These could be SCADA systems from multiple wells. Each well may have multiple meters recording production data. When we integrate this with a cleaning service, the service will essentially grab all these data streams. If you have, let's say, one well with multiple meters, it would compare the data between them and kind of filter out any anomalies that it sees in the analog data. It may also, if you see, let's say, you have a UDP connection, there's some data packages being dropped, then it will try to interpolate and clean the data as much as it can. Now, after the clean process, there's a data storage. You can imagine as the caching, because basically as this data is flowing in real time, the cleaning service will have, let's say, 2 threads. One that processes the data in real time, and another that will aggregate the data and send it off to a database. This database will aggregate historical data, so it may have well data from historical data from thousands of wells for many years. Plus, it's going to add the data that's flowing in real time. Once you have enough wells, then the clustering method will grab it, perform the clusters, and make it available for the predictor. The predictor is basically caching the curves, the cluster curves, and the real-time data and comparing to see if is the data within the expected threshold. And then finally, we have this service that basically acts as an interface with the visualization tool. So I'll go ahead and play this so you can see. So basically, looking through the different services. So within this service, we had an integration with, you can imagine any visualization tool like Spotfire, Tableau, whatnot. We built a very kind of simple visualization tool to kind of show these curves. We'll click on well 5, then we see the production curve, the production data flowing in. You'll see the orange curve right here is the prediction with the cluster, and there's a yellow curve, I don't know if you can see it down there. This is the decline curve analysis. So we're comparing the decline curve, the simple decline curve analysis approach. You can see the rates here in blue, the daily rates, and then the cumulative production is this curve right here. So we're keeping track of it. You can kind of see that the clustering method is more or less following the behavior of the curve, but the decline curve is a bit, it still hasn't kind of aligned well with the production data because there's not enough data. So we can fast forward real quick here. I'm flipping between different wells. We have 10 wells active in this use case, in this scenario. You can kind of see how it's flowing. Now, there's some interesting use situations here. As you can see, as I advance, there's one situation here where our decline curve approach didn't really match the curve well because it didn't follow the typical behavior. So our clustering method here is faring a bit better because it's deriving its predictions from other curves that were similar. And we can keep going. Yep, that's pretty much it. All right. So with that said, pretty fast demonstration. I can take any questions.
You have plenty of time for questions. Does anybody have a question? Yeah.
So do you take into account the pressure data, any pressure data, or just the production data of one phase? Or is it multiple phases or just one phase?
For this particular example, we're just taking production data. Now, there are use cases for example, when you're injecting frac fluid into the ground, you might want to observe certain anomalies in real time. We might take into account pressure in that case. But in this, we did a simple example just to showcase the use of Procrestes as a preprocessor, then clustering. You can apply any prediction algorithm on top of that and how that kind of remains as a kind of resilient solution over time.
You mentioned at one point that the curve wasn't exactly fitting and it would kind of update a little bit, and it was updating. What is like the minimum amount of production data required to get an accurate curve?
Well, I guess, so basically you can kind of see here that right around 25% it starts to stabilize a bit more. As time progresses, there's a greater confidence in the predictability. So maybe around 5% it stays pretty stable. So
Wait, I'm sorry, I don't know what percentages you're.
basically over time. So this is the lifespan of the well, around 25% of the lifespan around this point. It's pretty unstable. It's hard to predict where is the production going to go. Is it going to go up, down, and so on. But you might, let's suppose you're drilling a patch of land. You might have certain patches that say have high pressure, low yield. Others that have a high yield, low pressure, or high yield, high pressure. If they have a certain characteristic behavior when how they produce, then we can probably grab all those curves, kind of group them together, and then as we see the curve progress, we can kind of match it into the family curve where we think it would land. There are more improvements we can do with this. We can use a windowing technique. We cluster by windows, and then as we see the curve change location, we'll snap it up or down. We can also use geolocation to kind of guide where these family curves are lying. If there's a there's a consistency in the geo data, then we can do that. We could try applying different predictive models on each curve. So certain family curves might predict better with certain models, whereas others will predict with other models.
Thank you.
Other questions? Can you briefly talk about the software stack you use in the product?
I can describe it at a high level. Basically, a lot of the backend programming is in Scala and Python in the backend. The front end is React, and so a lot of JavaScript. The SCADA systems will have their own API, but in this example, we're basically mocking it. So we have historical production data, and then we spin up these services in the cloud, and then we can reproduce how it would have been if they were running. Yeah.
Any other questions?
Can you say something about your data cleaning and historical? I mean, you talked about the analysis, but I don't see how that's being applied in what you're doing here.
The data cleansing?
I assume that's where you're doing the Procrustes analysis.
The Procrustes is...
That's a cluster set.
Yeah, the Procrustes is just a preprocessor for the clustering process.
Say something more about that.
Which one, the cleansing or the clustering?
The clustering. The analysis, the Procrustes analysis here.
Sure. So basically, the Procrustes analysis is just, we're basically grabbing, here, I'll flip back to the slide where so imagine we have thousands of curves. You can kind of see it here in gray. Hundreds or thousands of curves. You use the Procrustes to basically move them into a common time interval. So we basically translate or rotate and scale them until they kind of match with each other. We don't flatten the curves. We don't smooth them. We just place them in a relatively similar space so that we can then apply clustering and get it out a family of curves that are characteristic. Once we have that, then we can start applying our clustering essentially becomes a bit more robust because when we're using k-means, for example, every time we run the k-means algorithm with different seeds, we might get different results. It becomes a bit unstable. So the Procrustes helps us to kind of stabilize that. And this is important with this data, real-time data that starts aggregating over time. And we want to keep it stable as we add more and more data. And let's say a service drops and we had to revive it, then we had to recalculate the k-means. It doesn't change with a different seed or whatnot. So once we have these curves, then we can apply, once we have the clustering curves, then we can apply a predictive model that's curtailed to a specific set of clusters, or we can just use a generic. In this case, we're using very simple generic predictive algorithm. Or we can use different approaches like I was mentioning earlier, slicing different windows of time into different clusters so we can, as we're moving along, we can redirect up or down as we see the curve advance. So does that kind of answer the question? Okay.
I don't know the subject matter that well, but I'm assuming you have multiple wells that you're modeling here for forecasting. That's what I'm assuming this data set is. Mm-hmm. How does it compare to the model you have to doing something like spatial temporal type model, or even general state space modeling, starting with that general form? How does that compare to what you're doing from performance perspective?
Well, we haven't experimented with a lot of models with this, but the general sense is, I mean, we kind of got a sense by, well, Hector looked through a few papers about this, and this is a general strategy that we can recommend data scientists to take a look. It's basically, if you're doing applying any clustering for any problem, try applying a preprocessor like Procrestes to put all your data into kind of the same domain per se, and then use your clustering algorithm to see how that helps kind of retain some resilience in your data.
Any other questions?
Hi, I saw the topic you're talking about the production from the physical based. So which means you probably have some physical models you built for the reservoir simulator. But from the slides, I only see some production curves. So do you think about like what the physical models like you really built and how you combine?
Yes, so originally the title, I guess in the print, it says physics-based, but we changed the name because it might be a bit misleading. We're not using, if we're talking about physics in terms of a simulator, we're not using a simulator for this. The physics is implied in the sense that we are preserving the physical characteristics of the curves, or the physical behavior of what we see. But yeah, there's no physics in this particular model, but you can potentially combine this with the physical model. But yeah.
Well, yeah. Well, I'm talking about this because when we try from the petroleum and reservoir engineer side, we prefer to have at least the synthetic models try to describe a reservoir. Then you can talk about the productions. I mean, your workflow is pretty good, and probably from one step you can consider add with some, at least just a very basic reservoir model, but could be, I mean, much better or more from the physical side to explain with that.
Right. I guess the main idea here is we're using a purely data-driven approach as a practical approach to predict production. We could use a physical model on the side, and then we can compare each, and then we can actually, potentially, if we see that they're both relatively close to actual, and we find that, let's say, averaging them together produces a better result, then we can use it that way.
Thank you. Let's thank the speaker again. Just a minute.